Log on, tune in, find out. Another good idea from Cambridge.
I'm not going to talk much about quiver varieties, but about character varieties, which are the multiplicative analog of this. And maybe I have time. If I have time, I will say a few words at the end. So I change a little bit what was the original plan. So I will first give some motivation. So the motivation here is from the character theory of the finite general linear group. So I will need some notation. So if X is an algebraic variety over an algebraic closure of a finite field, and F is a Frobenius endomorphism associated to some SQ structure, then we have the derived category of QL bar, so L doesn't divide Q, QL bar constructible sheaves on X. So then for a complex K in this derived category with an isomorphism between the pullback of K and K, then we define a function, the characteristic function of K phi. So this is, by definition, so this is a function which goes from, so this is a function which, so chi phi, this is a function from xf to ql bar, and that's an x to the sum of the I of the minus, or I, the trace of phi I x on the local cohomology set y x of k. So that will be the notation. So for the choice of phi, so I will not specify anymore, so that's why I will omit it, and it will be chosen so that everything I'm going to say is true. So then let G be a GLN of a FQ bar, and so we consider the standard Frobenius endomorphism, which go to Aij to Aijq. And we look at the ring, I mean the QL bar vector space of all functions from GF to QL bar, which are constant on conjugacy classes, f of x. Right, so now we have a basis that we will be interested in. So the first one is that of the irreducible character of GF. This is one basis, and the other one is made using the conjugacy classes. So if O is an F-stable orbit, F-stable conjugacy class, we denote by IC O bar QL bar. This is an element in this derived category. This is called intersection cohomology complex. And then we look at the function x. We will write it xO. It will be the characteristic function of this complex. So if O is unipotent, then since the value at, so say, a unipotent orbit parameterized by some partition. So then we have at a unipotent element given by another partition, that this is just a Koska polynomials. So this is a K tilde mu Q, and we have a Q minus L lambda. So, and if O is semi-simple, so this is a theorem of Lustig. the 81. And if O is semi-simple, then this is just the characteristic function of the conjugacy class O. That is, this is equal to 1 if X belongs to O, and this is 0 otherwise. So now we are interested, so they form a basis of this space XO, where O is an F-stable conjugacy class. And then we are interested in the two different ring structure on CGF. So the first one is using the convolution product. So the convolution product on the CGF. So this is defined by, for two functions on GF, this is defined by the sum of the yt equal to x of fy and gt. And then the otherwise is a pointwise multiplication, which is given by fg of x, so this is just f of x, g of x. So now we will be interested in the following ring. So CGF with a convolution product and we take this basis. So we can consider the structure constant of this ring. Namely, if I take two conjugacy class, I can look at the decomposition. So say ij, gamma, call it alpha, k, with sum over the k of x. Okay, so we suppose that we label all the conjugacy class. So that I call the structure constant of this ring with respect to this basis. And then we have another one. So this is CGF. Now the pointwise multiplication. So sorry, the basis is and the pointwise multiplication. So the character ring of CGF. And again, we have the structure coefficient constant. So we want to decompose this tensor product as a sum of beta ijk of ik. So we are interested in these two different constant structures. So first of all, the computation of this alpha ijk and beta ijk reduces to the computation of this coefficient. So the multiplicity of say yes. Okay, yeah, I need only three. So G, XOG, XOK, and the multiplicity of the characteristic function of the single element. So it takes 1 on 1 and 0 elsewhere. So here what I mean is not an inner product. This is, I will use this notation. So OI, OJ, XOK, by definition, this is the coefficient here. So this is really the multiplicity. And it's not an inner product, otherwise you have another coefficient. And then here it reduces to the computation of this constant. So now this is the identity character here. Right. So now what we want to do with that is the following. So really, the motivation from finite Lie groups is the following. So let's take any. So first, put I to be the number of conjugacy classes in GLN over FQ, and assume that we have a labeling, etc. So. And then the question is, can we find a map I to the set of irreducible characters? of GF. So explicitly a parametrization of the irreducible character by the conjugacy classes, such that we may write OI1, so OIK. So that is called, we'll call it alpha I1 IK of Q. And for the corresponding irreducible character, I mean, that is a question so far, so which I will call beta I1 IK of Q. And the question is, can we go from one to the other one by a deformation? So this is gamma I1 IK of Qt. So do we have a nice deformation between the two rings, basically? And what I mean by nice, so have something natural, because it's easy to construct such a deformation. So in particular, when those are polynomial, then we will like this to be a polynomial with integer coefficients and sometimes positive as well. So this is the kind of questions we're interested in. So why we came to this question is because, so this really, if it exists, I mean, and this is the aim of the talk, it has to be considered as a kind of Fourier transform in the group. So let's see what happens in the Lie algebra. So I will just say why we use this basis and not another one, and why these characters. So in the Lie algebra, so if you take G to be GLN over FQ bar, then we have a Fourier transform that I will not define because I will not use it. But a Fourier transform just transforms the convolution product into a tensor product. So the usual property of Fourier transform. And then there's a theorem that has been worked out by quite some people, including Lustig, which said that the Fourier transform of the characteristic function of the adjoint orbits, so the same, but now we work with the adjoint orbits, they can be written as a characteristic function of some character shields. So A is a character shield. So in particular, the multiplicity XO1 X OK in 1 now 0. This is exactly the same as the Fourier transform of XO1 X OK with the identity character. And these exactly are some characteristic function of character shield, which can be defined as in the group case. But we know that the characteristic function of the character shield in GLN, they are equal to the irreducible characters. This is also a theorem of Lustig, right? So the idea is in the Lie algebra, this structure constant are exactly the same because there's a Fourier transform. But in the case of the group, there's no Fourier transform. I mean, they are not the same, so we cannot have a Fourier transform. But by deformation, we may reconstruct some kind of Fourier transform. So that is the motivation. So now, what we will do, so of course, there's many questions about this deformation. If we have one, we can ask whether this coefficient will be the structure constant of some ring as well. And if there's a ring, does it come from some modular category, tensor category, and all these kind of questions which could ask. So the aim of this talk will be to give a geometrical description of these coefficients and also a combinatorial one. So now I will introduce the character varieties. So this is a representation varieties of Riemann surfaces. And we would like to construct this kind of object, polynomials, from a geometrical aspect and then a combinatorial aspect. And the conjecture will say that they are equal. Same construction. So by the way, I mean, even we can, we will see, it will maybe clearer later, actually. I don't want to talk about it now. So here, yeah, so we have to, what kind of?
So what is that limit? T goes to 1 and T goes to 0? Or what?
No, so I will say later. So here in particular, T will be equal to -1, but there will be natural specialization from a geometrical point of view as interest.
And what about the other one?
The other one, you will send the Qt squared to Q, and you will leave the other one to 0. So that will cause you take the pure part of this will be this one. Pure part in the Hodge sense. So we'll see. So you will have to see this as a Q. You have one. Well, I will explain this later. Right. So now I will introduce the character varieties or representation varieties. So we will work over the field of complex numbers.
What is G going to be?
What?
What is G going to be? What group is
It's GLN now.
GLN.
So it's GLN. So, I mean, for the other groups, it will be very difficult because we will see that for the combinatorial point of view, we will not be able to use the combinatorics. And the geometrical point of view might have a meaning, but we will discuss this later. So now G is GLN over C. And we take some adjoint, so K conjugacy classes of G. And then we can form the following variety. So we also fix a G which will be a non-negative integer. That is the extra, I mean, but it's still useful for what I want to do. So then we can form the following variety of a complex variety. So it's defined as the impulse, so B1, AG, BG. So I would say that at least from the geometrical part point of view, this is work with Tamás Hausel and Rodriguez Villegas. So this is part of the project that we are doing. So this is really the point of view of representation theory. But we have also other point of view that I'm not going to discuss. Then we look at this x1, xk. So this is in G to G cross O1. So we take the Zariski closure, OK, such that the product of the commutator from I to 1 to G times the product of the conjugacy class, means the element in the conjugacy class, is equal to 1, identity. And we take the quotient by G. So here the quotient means the spectrum of C of U of the invariant ring. So U is the top. So this is an affine variety, complex variety. And we call it a character variety because we can identify it. So if I take a Riemann surface of genus G, Riemann surface, then and K point on this Riemann surface, then I can identify this variety. So O1, OK, with the set of homomorphism from the fundamental group of S by taking out the points into G, such that the single loops around the punctures are sent to the prescribed conjugacy class in the Zariski closure, and we take the quotient by G. So that's the meaning of that's the terminology of character variety. So it's representation of the fundamental group of punctured Riemann surface. So now we need to have we will make some assumptions. The first one, it's an obvious one, otherwise the variety will be empty, is so it's an assumption on these tuples. So we want the product of the determinant to be equal to 1. Otherwise the variety will be empty. And the second condition, we want the following thing. So for all subspace of Cn, stable by some xi in OI, so for each I, then we want that the product of the determinant, such that, the product from 1 to k of the determinant of the restriction, xi to v, is equal to 1. So if this happens, then v, we want v to be 0 of V to be the whole space. So this, in that case, we say that O1 of K is generic. So that will be very important, and you will see why. Right. So I will give some examples of generic conjugacy classes. So I will list this here. So for instance, if we take some examples, so if I take one conjugacy class, so say zeta, 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 so a central element, then and such that zeta cube is equal to 1 and zeta is different from 1, then this pole is generic. Why? Because the total product, the determinant, is equal to 1. But if I take any subspace which is stable by some element there, then the determinant will not be equal to 1. So partial product of the eigenvalues will not be equal to 1. So in that case, this is what we say generic. There's another case, so it's very easy to construct generic conjugacy classes. So I will give another example. So if C1 is conjugate to, say, 1 like this, so minus 1, 2, C2 is conjugate by, say, 1, 1. Maybe I should. And C3 is conjugate. So now I have to be careful. So I have to avoid to have a product being equal to 1. So I cannot choose 1, but I can take 2, for instance, 0. 2 is also safe. And then I just take the, I make the word product. So this is, so we say less 1, this is, so that is generic then. So C1, C2, C3 is a generic tuple. So basically you can take everything you want for the first ones, and the last one you have to be careful. So that you have this kind of inequalities which defines the genericity doesn't occur. So, so I will need also to talk about the type of a conjugacy class, So if I choose a conjugacy class, so type of a conjugacy class in GLN over C, so I choose an element in O. I look at the centralizer in G of its semi-simple part. So this is isomorphic, so it can be written as a sum, as a product from 1 to S of some GL of Ni over C. And then the unipotent part, which live in the centralizer, will define a partition for each Ni. So XU defines partitions omega I of Ni. So then we can choose the total order on the set of all partitions, and we consider the non-increasing sequences. Actually, so we assume that this is order scale, and this is called the type of O. So basically, we just forget the eigenvalues. We take the Jordan form, and we forget about the eigenvalues. We are not interested in the eigenvalues. So then we can define T of n, the set of all omega S, such that omega I is a non-empty partition, and the sum of all the total size, the sum of the size of the partition is equal to n, so that be the set of types of size n. So any type of size n can be realized as a type of some conjugacy class. Right, so now we have that it will be very convenient to work with types for the following reason. So first we have the following proposition. So if omega equal to omega 1, omega k is a multi-type, so Tn of k, then I can always find a generic tuple of conjugacy classes of type omega. So I can really think, in what I'm going to say, actually, we will really think in terms of types and not of conjugacy classes, because we can always realize a multi-type as a type coming from a generic tuple of conjugacy class. And the next conjecture says why. So I heard it in a talk of Nakajima's, at least for the semi-simple case. So if omega is a multi-type, and if I have two tuple of prime of same types, generic of same type, omega, then what is the connection between the two character varieties? I cannot put it off. So then you have the following conjecture. So if I take the intersection cohomology on these character varieties, the first one, okay, with complex coefficient, and the other one, M O prime 1 O prime K, then they are isomorphic as a mixed Hodge structure. So I will recall what I mean by that. But this is, since we will be interested in the various filtration in this cohomology, we only care about types and not about conjugacy classes. So we will write, so for the this justifies the following notation. We will write, instead of M01 OK, we will write M omega, which will be easier to have the notation. So, so now I will review a little bit about mixed Hodge structure and how we can study them using arithmetics. Because we start from complex varieties, but after we want to do something of a finite field, so we have to make a connection. Yeah. Well. So so first, a Hodge structure of weight K is given by the following data. So we have a rational vector space, finite dimensional vector space H. And the second one is we can, if we have the following decompositions. So there's a decomposition. So H PQ, so that P plus Q is equal to K, and the complex conjugate of PQ exchange the QP. So for instance, if X is projective and smooth, then we have the usual Hodge structure on the complex variety. This is Hodge structure of weight K, where K is the degree of the cohomology. But in the case it is not smooth, not projective, sorry. So we have we can define this mixed Hodge structure, which were defined by Letellier. So we have this mixed Hodge structure on the cohomology of HKXC. So I will take X smooth. Actually, it was defined also when X is not smooth, but we will need only the case when X is smooth, even we'll see that later. So this is a filtration in this case. So which is called the weight filtration. Such that each quotient, so the gradient of Wm, which is Wm over Wm minus 1, is a Hodge structure of weight M. That is called the pure part. So in the case of projective and smooth variety, we have all these are equal to each other, and we have only the WG. So we have equality here instead. So this is Right, so we call this the dimension of this HPQ, called the dimension of HPQ here. They are called the Hodge numbers. So then you can define the mixed Hodge polynomial, which is what we will use. So first, h of I, g, k of x, they are the what's now mixed Hodge numbers of hkx. So basically this gives you the weight, so a plus g is the weight. And it tells you where it lives in the filtration. So then you can write the Poincare polynomial of this. And this is what we call the mixed Hodge polynomial. So this is the sum of all the ijk of I, h, I, g, k, x, and you have one variable for each integer here. So when x is projective, then the sum is over the I plus j is equal to k. Right? So that is the difference. So I should say something. So for the pure part here, so the pure part, so that matters for the question of before when we take the pure part of some polynomial here over there. So the pure part of hk of xc is by definition wk. And this is also can be realized as the image of the cohomology by the smooth compactification. So when this morphism is surjective, it means that the variety is pure. All right, and so now I should say as well, so we have also a mixed Hodge structure on the compactly supported cohomology, which actually is the one we will use because it has better connection with finite fields. So in this case, we can then define the compactly supported mixed Hodge polynomial, sum of the ijk of hc jk of x, and same story. So we just put here to write the compactly supported. So then we have a relation between these two polynomials. We have a Poincare duality when x is of pure dimension d. So in particular, we can write hc x yt as x yt squared d, and then h x minus 1, y minus 1, and t minus 1. So this is when x is of pure dimension d. And this is a Poincare duality. So now I'll give an example how to calculate, in a very simple case, this mixed Hodge polynomial. So if you take x to be a C star, so then you know that the Betti number, so you have h0, which is equal to 1, the dimension of the h0. You have h1, which is of dimension 1, 2, and h2, which is equal to 0. So now if you look at the filtration here, it tells you that the weight can vary between j and 2j, where j is the degree of the cohomology. So for the first one, you can have only h0, 0, 0. Right. For it's 0, between 0 and 2, 0, there's not much space. And here you can write as all the possibilities. So you have h0, 1, plus h1, 1, plus h0, 2, 1, plus h2, 1, plus h1, 1. So here these are of weight 1, some of these things are of weight 2. The thing is, if this one is non-zero, this one will be non-zero and they will be equal, because the complex conjugation exchange the weight, right? So they exchange the indices. So since this is equal to 1, I cannot have sys1 because otherwise I need sys1 as well. So, and same for here. So I have only h11, which remains. Right? So then the mixed Roche polynomial is, in this case, this is just, so this is 1 plus x, y, t. If I want to take the compactly supported one, so this is, you apply the above formula, and you have t plus x, y, t squared, in this case. So now you can notice something. This one is interesting, have some consequence in, some specialization can be calculated. So this is what I will talk about. So then, if you take this specialization, so in the same example, and you put -1 here, so then you have xy minus 1, right? And that you can write it as p of xy, where p is this polynomial, t minus 1. Then if you look at the number of points of x over a finite field, fq, then this is q minus 1, and this is pq. So in this case, we see that this specialization of the mixed Roche polynomial actually computes this number. Right? And now we have something more general, which is a theorem due to Katz in 2005, which says the following. So if you have a variety, algebraic variety of a C, so which is polynomial count. So I will say what it means. Polynomial count. With counting polynomial P, say, P. So what does it mean? It means that for all P large enough, the number of points, so I skip some details, all right? Not talking about how to change from a field to another one. Actually, I skip the detail, but you can, it's very general. You don't have, X has to be quasi-projective, and you don't need X to be smooth or nothing like that. So this is a very general statement. So then, it says that this is what it means to be polynomial count. So in particular, the polynomial doesn't depend on the field you choose. Right? So the characteristic has to be large enough. Then the specialization of the mixed Roche polynomial xy minus 1 is exactly equal to pxy. That's what it says. So in particular, so in the example for C star, this is what happens. This is, for instance, true if you take X to be GLN. This is a true statement. This is polynomial count, and then you can compute the polynomial count, the polynomial which counts the number of points of the GLN over a finite field is given by the mixed Roche polynomial. So you can work out the specialization. In particular, it says as well that this polynomial depends only on the product xy. So it gives you this following information. So if I write what is h, say, x, xyt minus 1, sorry. So this is the sum over the ij, the sum over the k of minus 1 k h c I j k of x. And then you have x I y j. So saying that it's polynomial count, it says that if I is different from j, then this has to be 0. So in particular, so so if x is polynomial count, this implies that this sum over the k of minus 1k hci j kx is equal to 0 if I different from j. It doesn't mean that these Hodge numbers are different when I is different from j. It says that you can have cancellation. And actually, Cass gave an example where this, you might have I different from j here, but you have indeed a cancellation. So that is also useful. So I'll just say an interesting corollary as well. If x is polynomial count plus x is pure, meaning that in the cohomology, they're all equal to the wj, right? You don't have this, you have a trivial weight filtration. So if x is pure, then you can say something more. You can say that h, x, xy, pure means that the sum has to be equal to k, otherwise 0. Right? So in particular here, you can work out k should be I plus j, and so you can really say something. So in that case, this is equal to the Poincare polynomial for the compactly supported Poincare polynomial of x, and you take q. And this is actually the sum of the IHC I 2I. So all the mixed Hodge number of this form, and the qi, I think, well, maybe q2i, I would say. I put the x somewhere, so I should write it like this, maybe easier. So I can take the square root of q, and then this is just qi. So it says that all the mixed Hodge number of this form, hi 2i. So if you have pure plus polynomial count, the mixed Hodge structure is trivial, there's nothing. So for instance, it tells you that, without knowing very much, that elliptic curve cannot be polynomial count, otherwise it will not have h odd cohomology, for instance, say something like that. Let's say that in particular you don't have odd cohomology.
This cancellation that you mentioned possibly could happen.
Yeah, exactly. Yeah. It can have, yeah. This one here. Yeah. Without the I, you can have I and j different, and you can have a cancellation. So let's give a counterexample. But if it's pure, then it's even more trivial because the wave filtration and the Hodge filtration are all trivial. So for instance, quiver varieties are mostly pure and polynomial count. So you can work out the Poincare polynomial by counting the number of points of a finite field. So that's an interesting aspect. The character varieties will be polynomial count but not pure. So it's not, so you have you have to do something. So now, so what about if x is not singular? So if x is singular, you can define mixed Hodge structure on the cohomology, but this is not what we want to do. We want to we prefer to use so what Saito did. So you can define a mixed Hodge structure on the intersection cohomology of x. So same way the notion of definition of mixed Hodge structure is very general. So you can do that, and then you can define the mixed Hodge polynomial. So I use a compactly supported one directly. So x, y, t will be igk of h. So that is the mixed Hodge number for the intersection cohomology. X and xi, yj, and tk. So, of course, if x is smooth, then it's the same Hodge structure as a mixed Hodge structure as the one of the link. So now we want to have, we will need this theorem of Cat, I mean the analog for the intersection cohomology. So, to show that I didn't forget anything. So, but we specialize for character varieties because the general case you have too much assumption and it will be too long. So, yeah, I should leave this one. I want to compare. So then, theorem. So let's take, we take O1 OK generic of type omega. And then the theorem says that there exists a polynomial in Zt. So in particular, the character variety, unless the conjugacy classes are semi-simple, it is singular. If the conjugacy classes are semi-simple, it's smooth. But if they are not semi-simple, then it is singular. So we use the intersection cohomology. Then there exists P such that the sum over the X in M omega, so you have a reduction of a finite field, of the characteristic function of the intersection cohomology of M omega over a finite field, so Zariski closure, QL bar evaluated at X is equal to P of X, is equal to P of Q, sorry. So for Q large enough, same. And moreover, so the specialization of this mixed Hodge polynomial M omega X y minus 1 is equal to P xy. So I just want, this is a generalization. So it's not true for any variety. I mean, you need actually to have a desingularization which has polynomial count, and so that you use Katz's theorem. Again, this is kind of trick you need. What I want to point out is that if the conjugacy classes are semi-simple, okay, are semi-simple, then the character variety is smooth because they are generic. So I mean, I didn't say that before, but it's smooth, and therefore, if you apply this formula, so the intersection cohomology is just a constant sheaf. So the intersection cohomology is just a constant sheaf. And then the left-hand side of 1. So the left-hand side of 1 is just a number of 1. So then is equal to the number of points of M omega of a finite field. And then this is exactly Katz's theorem. Right? So when it is smooth, that is exactly you get it from Katz's theorem. So now we are very close from here, just to have one specialization from here. So we have, I will state.
So is the first part of this just proven by counting?
How is it proved?
Yeah.
This one? You prove it from Katz's theorem by taking a resolution. And then you have some stratification and you do some kind of induction using Katz's theorem. This is basically what you do. And you check that this is okay. So now, there's a corollary from this theorem. Corollary. So the specialization of this mixed Hodge polynomial, M omega x square root q minus 1. So since it depends only on the product xy, you can put square root q and square root q. Then this is equal to 1 over PGLN of a finite field of exactly what we have. So this is alpha 1 k of q. And you can prove that. So you have one specialization. If you sum t to minus 1, this is. So that you write it as m omega qt. You don't need to have two variables because of this theorem. Depends only on the product, so you may just have one variable. So it means that if you take, sorry, it was, minus 1 here. So now there's a conjecture, is the following. So we modify a little bit the coefficient here. We take 1 over the cardinality of PGLN over FQ. And here we take Q times the dimension over 2, the dimension of the variety. And then the conjecture says that this gamma 1 k of qt, they are equal to this hc of m omega qt. So I will discuss a little bit about this conjecture in a moment. I need to give a formula for this one, because now we get a combinatorial formula. And from this combinatorial formula, we will be able to prove this conjecture in some cases. So that is true if G is equal to 0, the genus here. So what I said before, it works for any genus, but here it makes sense only for genus equal to 0, otherwise you have to add some stuff here and here, which is not so. So now a formula conjecture, a formula for this one, for gamma 1 k qt, and that is defined in terms of the McDonald polynomials. So really now we work, so we have to know that we do all what we are doing is for generic things, generic conjugacy classes, generic characters, whatever it means. If it's non-generic, we don't know what happens.
Emmanuel, how do you go from this convolution of these?
And here?
How do you get to the quiver varieties? I mean, character varieties just from the function class. I mean, in the character varieties also this other G, at least A1.
Yeah, but
AD.
I say G equal to 0 now.
Oh.
In this case, but I still need a G to explain, but why we can prove still something. I mean, it's just to the G will still be useful, but for something else.
Also, in this corollary, the G is
No, that's true. Oh, here, yes, of course. Yeah. So now, but I will say, I mean, I will give you an example where we can prove a more general conjecture with G, which will not be equal to 0, and this is the only case where we can prove something. So I will need at some stage that J is different from 0. So now I will give a combinatorial formula for this one, which has the right specialization. So it takes the pure part. So in terms of mixed range polynomial, it's clear that now this one will be attached to some H1, 1, 2, something like that, right? So that is pure, and all the non-pure part you throw it away, and you expect to end in here, right, from the mixed. Okay, so let me give a combinatorial formula. So you take a K separate set of infinitely many variables. So sets of infinitely many variables. So we have one attached to each puncture or to each conjugacy class. And then you consider the ring. So you take the Qt of symmetric function in each of these, which are symmetric in each of these variables. Right? So they are not symmetric. I don't take the union. It's a separate. They are separately symmetric in each variables. And then you can so then we consider, we define this omega qt, which is defined, so you take the sum of all the partitions of some h g lambda qt, so the genus appear here precisely, and then you take the product of all this symmetric functions, so q squared, t squared. So these are the modified transform version of the McDonald polynomials. So they are the sum of the nu of the qt cos square polynomials. And then has a sure, so this is a sure nu. So what is important here that this is, the punctures appear here, the I is here, right, only on the set of variables. And that is kind of deformation of the Hooke polynomial that I will not discuss because that will take. So then the formula is, so we can define the, another thing. So if we have a type, say a type is something like that, so omega 1, omega 2, omega s. Then I define S omega to be the product, so S omega 1 x, so on S omega S x, and that is a sure function, symmetric function. So the total product is not. So then we define H omega qt to be this inner product. So this is q squared minus 1, 1 minus t squared. And so the inner product is defined like this. This is the whole pairing. You do it on each lambda xi. And then you take this one, so the product of the S. So this is a so it's not very good notation, sorry. Because I use it for two different things. So this is just... so omega is a multi-type, T and K. And then I make the product of all these functions, so from 1 to K, S omega 1, sorry, 1 is not a partition, it's a type, x1, xi, sorry. I will write xi like this. And then I take the log of omega qt. And I take all this pairing. So the log is a kind of inverse of the exponential, which, and capital E, which is defined like this. You can define as the exponential. As for the zeta function for curves, for instance, to infinite of VQ R over R PR. So you have with a capital E, and this log is just the inverse of this map. So just leave it for the details. And then so the theorem is that the theorem is that our gamma 1 k qt is equal to there's something no, that's right, h, oh yeah, so there's a square root qt power the dimension of h omega minus 1 over square root q and t square root q. So that has the right specialization, and it is a polynomial with, I mean, we cannot put it a polynomial in general, but when we get calculated, it has integer coefficients. And so the conjecture, so that is for genus 0, again. And the conjecture is that this mixed Hodge polynomial is exactly this one, but for any genus. So now, so that is the same as the conjecture over there, except that here we have really a combinatorial description of this gamma I. And then it is proved, so this is true in the following cases. If j is equal to 1, k is equal to 1, there's only one puncture, and you take this partition, n minus 1, 1. So basically, you can draw a quiver if you want. This is n, 1. Genus is a number of things. So this is a semi-simple conjugacy class whose where the multiplicity of the eigenvalues are given by this partition. So that corresponds to a semi-simple conjugacy class. And in this case, we can prove it because this variety, so m omega, so it's smooth. I mean, it's semi-simple, so it's smooth. It is you have an isomorphism with the Hilbert scheme as a mixed Hodge structure. So of course you don't have an isomorphism between the Hilbert scheme and m omega because this one is not non-affine and this one is affine. But you can prove actually that you have a deformation of the complex structure, and it's still you have a mixed Hodge. They are isomorphic as mixed Hodge structure, and the mixed Hodge polynomial of this Hilbert scheme was computed by Sorgel and Goltzke. So Goltzke and Sorgel. So actually, using their formula, we can compare with our conjecture, and it agrees. That's why we need the genus 1, because we cannot do it with 3 punctures. So that makes this conjecture reasonable, maybe. So I will stop here.
structure, they are also isomorphic to moduli with the X bundles on parabola on some modular space.
Sorry?
These spaces that you consider.
M omega, yeah.
Yeah, they are. If you change the complex structure, they are spaces of X bundles or some parabolic type. For example, if the omega are all equal to 1, these are really the X bundles. These spaces. You don't.
Oh, Higgs bundles. Yeah. I mean, yeah. Well, you have. Yeah. You're right. No, exactly. Yeah, exactly. That's right. That's right. Yeah.
So
that's the part I don't know very well, but my collaborator Hausel, is studying the connection with Higgs bundles. Yeah.
So is there a comparison between the two Hodge structures?
Yes. So it is expected that they will be the same.
Like in this.
Yeah. Exactly. Yeah. So these kind of questions are very tricky because there's no isomorphism. They are diffeomorphism, but they don't preserve mixed structure. This is something algebraic.
Yeah. It contains a lot of compact subvarieties.
Yeah.
One is affine, so.
Yeah, exactly. Yeah.
Any other questions or comments? So if not, let's thank the speaker again.